So the previous talk, right, told you maybe, okay, if we have these large-scale quantum simulators, what kind of questions can we answer as condensed matter theorists by using them? But of course, we also know that we shouldn't only be asking what can quantum computing do for us, but we should also be asking what can we do for quantum computing, right? And, well, we can do a whole lot, it turns out. And this will be the topic of my talk, which is the miracle that is quantum error correction. And I hope I will convince you that it is indeed surprising that it works, but it does work. And this is really the reason why we can have any hope of building these machines. Okay, so you should know your enemy, but you should also know what you are protecting. So let's talk about what is actually classical and quantum information. So classical information is maybe a bit dull. It's zeros and ones. This is at least the unit that we usually use is the bit, which is just a 0 and 1. And your computers, right, your phones in your pockets, they all internally calculate with strings of zeros and ones. And zeros and ones are okay. They're either 0, 1, yes or no. If you have in Schrödinger, maybe your cat is dead or alive. And maybe you're already seeing where I'm getting here with quantum information, because quantum information is much more subtle. So quantum information, like the minimal information to describe, needed to describe a quantum system of 2 levels, like an atom of 2 levels or something similar, is a qubit. And a qubit can not only be in 0 and 1, it can be in a superposition, we say, right? And as we write mathematically as this kind of, well, it's a vector technically speaking, where we can write it as alpha 0 plus beta 1, where alpha and beta are complex numbers, right? Their magnitude squared has to sum to 1. And I can like visually represent this kind of state on the so-called Bloch sphere. You might remember seeing this picture in your quantum mechanics class, right? And it means that I can associate basically every combination of alphas and betas that describe a valid quantum state with some angles like this. And then I can identify each point on this surface of the 3-dimensional sphere with one quantum state of a single qubit, right? So this is much more complicated than this 0 and 1, right? Actually, there's a continuity of states, right? At any point on the sphere. And it gets even weirder when you think about how we as classical beings interact with this quantum information. Because now, right, if we want to look at something, right, look at the qubit, we have to measure it. And it turns out if we measure this thing, then it is indeed, with certainty, afterwards, it is with certainty 0 or 1, right? So we get a probabilistic outcome, right? We get 0, 1, yes or no, dead or alive, with probability alpha squared and beta squared. So there's a probabilistic outcome. But after the measurement, the state of the qubit is fixed, right? So once you open the box, Schrödinger's cat is dead or alive. It's only both as long as you do not look. And this weirdness, in fact, can be utilized, right? This is, of course, why I'm telling you about this today, right? And actually, the way it can be utilized, right? Okay, Alessia already told you a great bunch about these things. But I want to say, okay, actually, the very first people to think about, or some of the very first people to think about the problem how to utilize this weirdness of quantum mechanics actually were in Oxford. Deutsch and Josa published the Deutsch-Josa algorithm, which is kind of a toy problem in some sense, but it was one of the first problems that actually did establish that quantum computers can solve problems that classical computers cannot solve. And then, of course, Shor, Peter Shor from MIT came along in 1994, and he published his prime factoring algorithm, which is maybe the most famous application, quote unquote, that we have today, at least for exact quantum computers. But I also want to say, for example, Andrew Eckert, for example, here in Oxford in the math department, he, for example, was the first person to think about using quantum computers not for breaking encryption, but for actually encrypting things very safely. Right, so this is quantum cryptography. And each of these topics, honestly, would be a 45-minute lecture on their own. So I will not talk about that much more. You're happy to ask me afterwards. But what I will instead try to tell you is how can we implement, or how can we protect this information? Because if we want to use it, we have to be able to store it in some way. Okay, so maybe before I go too deep into this, how do present day quantum computers look like? So what is the quantum information? Maybe the most similar version of quantum computers to the machines we today call classical computers is the superconducting qubit machines, right? This chip, for example, from the Google lab, it looks kind of like you would expect from a silicon processor, although it's made actually from superconducting aluminum instead. For example, I mean, this is a very rich platform. So for example, in Oxford, these kind of devices are built by the lab of Peter Leek. This picture is from Google Quantum, and there's, of course, major industry players now, Google Quantum, IBM Quantum, Alice and Bob being, for example, a startup from France. So these things also are now get into the startup space. But of course, the pioneering work, for example, a lot of pioneering work was done in academia, mostly in the Yale Quantum Institute, and partially also at ETH Zurich, at the Quantum Devices Lab there. So then another major platform is trapped ions. Alessia already mentioned them. This is actually a picture of a trapped ion taken just in the basement of the Beecroft building in the lab of David Lucas. It's very beautiful. It's actually captured with an iPhone, I believe. And if you would zoom very closely, you do actually see the atom. This is kind of fascinating, right? And this is an ionized atom, so you trap it with a magnetic trap. This is why we call them trapped ions. And okay, actually, these was historically the first platform where quantum computing was performed, right? David Wineland, who was at NIST when he performed the work, received a Nobel Prize for that in 2012. Today, of course, there's again major industry players, Quantinuum, who has still close relations actually to the University of Oxford, especially the computer science department here, and then IonQ, I think being actually the quantum startup with the biggest market capitalization, I think. So it was, I think, the first quantum unicorn. I'm not sure they're still that valued, but they were at some point. So, another platform, Alessia also already mentioned that, are reconfigurable atom arrays. So right here, the atoms are neutral, and you trap them with a laser beam with something called an optical tweezer. And actually these, I mean, right, this is maybe a more boring simulation than the Mario that was shown before. But if you want to do computation, this is more like what you will do, because you see that there's like these arrays, and they get brought close together basically on demand when you want to perform a gate. When you want two qubits to interact, you bring them close together physically. And otherwise, you have them far apart. And this is kind of fascinating, has created a lot of crave recently because of this great flexibility. So this is a really promising platform, maybe that's emerging right now. And this also means that there's, I mean, at the moment, I would say there's one major player, which is the laboratory of Mikhail Lukian at Harvard. And they have also founded a company, which is Q-Era Computing. There's a bunch of other platforms. All of them have advantages, disadvantages. I won't talk about these too much. There's photonic quantum computers, there's quantum annealers, there's spin qubits, actually Quantum Motion, a major player in spin qubits, also again being founded actually at Oxford in the material science department by Simon Benjamin. And okay, so there's a lot of platforms that all have promises, and none of them works just yet. And this is because all of them share one simple problem, and that is noise. Right? Quantum states are inherently fragile. And this is really also, of course, the reason why we don't see quantum mechanics around us, right? Because quantum mechanics is fragile. Quantum information decoheres and it becomes classical. So in the end, if you scale things up and you do it without being very careful, right? That is to say, it becomes just classical information, right? And, well, hopefully we convince you that there is a way to do it to prevent this classification of the quantum information. And maybe to really drive the point home of how important this is, let me tell you then thing that is not often appreciated, which is that quantum computing is by far not the first alternative idea to implement computers beyond classical ones, or beyond the ones we build today. For example, my fellow German, Arnold Schönhagen, in 1979 published this beautiful paper on the power of random access machines. And he basically asked the question, imagine you had something, well, called a random access machine, which is basically a computer that operates on floating point arithmetic. The idea is that you have a memory that instead of bits stores floating point numbers of arbitrary precision. right? So it's not something we can do if we, on a computer, if we have a finite memory, right? This is why it's different. And he imagined also, imagine now you had this floating points that you can store, and you can also perform arbitrary arithmetic on them, again with arbitrary precision, right? His idea actually, I think, was basically to build an analog computer based on some, I don't know, some wire, some coherent, I think some oscillations in a tube or something like this, right? Right, which then would correspond to a continuous number. And then he proved, okay, if you do this, right, actually then these random access machines would be vastly more powerful, even than the quantum computers we try to build today, right? So for random access machines, P is NP, if that tells you anything. What it really means is that you can basically really solve optimization problems, you can solve traveling salesmen, all of this in polynomial time. That's the idea, right? So it would be extremely powerful, but they have never been built, and why is that? Because of noise. We have just not figured out a way to do floating point arithmetic well enough, right? There's no known way, there's no known way to fault tolerantly implement these machines. And the surprising fact about quantum computers is that they can be implemented fault tolerantly. Okay, so maybe before I talk about quantum computers, let me tell you, okay, what does work anyway? So we want to protect classical information maybe first. Let's start with that. Let's start with sending a bit, right? So imagine Alice comes into a bar and she wants to order a coffee at Bob. Alice and Bob are the names we usually give to these two people in computer science. And she said, okay, I want coffee. And then there's some noise, and actually Bob misunderstands her and here's T, and she's getting a T. And this happens with probability P. We can formalize this by saying, okay, you're sending a 0, and with probability P it flips. And with probability 1 minus P, it doesn't, right? So this is the formal version of that. And there's one simple form of error correction that we all do intuitively in a noisy bar. We repeat ourselves. And in computer science, this is called the repetition code, right? So instead of saying, I want coffee, I say, I want coffee, I want coffee, I want coffee. And they'd say, okay, if Alice says that 3 times, and Bob misunderstands her once, he has tea, coffee, coffee. And this goes like, okay, I guess she meant coffee, right? Again, the formal version of this, you implement the repetition code, so you define something called a logical bit. And the logical 0 is just n times 0 in this times. And here n is 3. You take n times 1. And if noise flips half of your bits, right, then you can do something called majority voting. That is, you ask, are there more zeros and more ones in the message I received? And you just assume it was, the original message had all ones or all zeros, right? And well, the failure probability then is lower because, for example, right, if this can still go wrong if Bob actually misunderstands you twice. But of course, this happens with probability P squared. And if P is small, P squared is smaller than P. Right, so that's the idea. Right, so error correction improves the fidelity of classical information, even if you send it through a noisy channel. That would be maybe the formal statement here. Okay, but quantum error correction, so really people in the early 90s thought it was a futile effort. And there's a bunch of reasonable objections to quantum error correction being possible. And maybe the most damning one is we cannot copy quantum information. And that seems to be a major objection to what I just told you, that, okay, how do you protect information? You copy it and send it multiple times. But for quantum information, actually, we cannot do that. And the proof is very simple, so let's attempt a proof. Okay, it goes the following. We will prove by contradiction. So imagine you could do it. Right? Imagine there was an operation U. This is some unitary matrix that acts on 2 qubits. Right? We want to copy an arbitrary state psi into this state E. E can be whatever, 0, whatever. And then after you apply the operation, it has to be psi psi. And this has to work now for arbitrary states, right? Because our copy machine should copy whatever, right? Then we can write the following, right? We can rearrange this. So I'm working in bracket notation here. I hope you do somewhat remember. But what it means really is, okay, we consider the overlap of 2 states, phi and psi, and we assume that both of them can be copied by our machine. Right? And then this is just the overlap. So this is, right, it will be 0 if they are very different, and it will be 1 if they are the same. And then what I can do is I can insert this U dagger U here, which is just the identity. This is just to say, okay, quantum operations are unitary. This is mathematically the precise statement. But then I can also say, okay, now I can imagine this acting to the left and this acting to the right. And what I will get is psi psi and phi phi. And this, of course, is again the overlap, but squared, because now I have it twice. And okay, so we have proved that the overlap between the two states is equal to the square of its overlap. But there's not a bunch of numbers. There's not many numbers who are equal to their square, right? There's two of them, actually. This is 0 and 1. So either the states are identical or they are orthogonal. But they are certainly not arbitrary. Right? And that is a simple proof that a sensible quantum operation, a unitary time evolution, cannot copy quantum information, at least not arbitrary one. Okay, so that is bad, but it gets even worse. The square. So measurements are destructive. I told you, right, after you looked at the cat, right, it's not dead or alive anymore, right? It's either the two, but it's not both, sorry, that way, right? That means, okay, we measure this thing, we measure z formally, so we are asking, is it 0 or 1, right? And then it will be 0 or 1 with the respective probabilities. And that, well, so how do we do majority voting then, right? I told you, right, you look at what you got and you will look what you got more. But now you cannot look at your state because it will destroy it. That again seems very bad. But it gets even worse, right? Because also the errors are continuous, right? So I told you the state of a qubit is can be identified with this point on the three-dimensional sphere. But of course, errors are arbitrary small rotations then, right? Any sensible operations, right? This is why it's unitary, right? It's a rotation on the sphere. And of course, now this can be arbitrarily small. And this starts to look a lot like this floating point problem, right? Where we cannot even do floating point arithmetic correct. How can we do that correctly, right? It seems like very, very, very bad. But again, surprisingly, now, I hope you now get the surprise of people that really happened when in 1994, Peter Shor and actually independently Andrew Steen of Oxford University showed that quantum error correction is indeed possible. But what I want you to appreciate is that we really need all the weirdness and the beauty, I think, of quantum mechanics to make it work. So we will need everything. We will need entanglement, we will need measurements, superpositions. So yeah, so buckle up, and I hope that I will try to explain to you how it works, right? And I will lose the Shor code, because for the Shor code you have to, for the Steen code works just as well, right? And I would love to explain this to you because we're in Oxford. But unfortunately, you need a bit more information theory background. So I think Shor's is a bit more intuitive, I'm afraid. But okay, so let's do it. And let's start with the quantum repetition code. So what's the quantum version of our repeated coffee order? And the first observation is that cloning is not necessary, because we can do entanglement instead. Okay, so Alessio fortunately already did some circuits. So again, just to repeat, right? So each horizontal line here in this diagram, right? This diagram presents an operation on a quantum computer. Each horizontal line is a qubit. Here we have an initial state, and this is a gate. And the gate is called the C-NOT. It's a controlled NOT. This gate actually makes perfect sense classically, right? It just says you apply a NOT to this qubit if this qubit is 1. And you don't do it if it's 0. Right? So that means, okay, if this is 0, 0, if the input would be 0, 0, right, the output would be, again, 0, 0. If the input would be 1, 0, the output would be 1, 1. Because the first bit basically indicates whether I should flip. So now this is a quantum computer. So it gets a bit more complicated than that, because I could get as an input, right, I can put a superposition of things. And how does the gate act then? We get this by linearity. So we can think here about what happens to each term. Oh, this pointer is not, okay. Right, we can think about what happens to each term separately. And we can, okay, if it's 0, right, I already told you, 0, 0 becomes 0, 0. And this is the output, first output term. And then here there's a plus beta 1. And okay, if the first qubit is 1, the second gets flipped, so the output will be 1, 1. And this is the second term in the output. Okay, I hope this is somewhat clear. But the important thing is now that the output indeed looks a bit like a repeated information, right? Because I've not copied, but I've entangled the two qubit, right? Entanglement here means just that, okay, on the left-hand side, you see I can write the state of the two qubits separately. On the right-hand side, I have to write this joint state, right? This is what I mean by putting it here. So we produce redundancy by entanglement instead of by cloning. And then the quantum version of our redundant T offer is just we make two with this twice, right? So we copy, we entangle psi with a second and a third qubit. And this now will be our logical quantum state of the quantum repetition code. This is not yet, we are not that yet, but we are getting there. So what about measurements? So I told you measurements are another problem, right? So you see already I'm going now one by one through our objections. What about measurements? Okay, we have this logical state, alpha 0, 0, 0 plus beta 1, 1, 1, right? This is a superposition the superposition and an entangled state, right? And imagine you measure now Z1. So you ask for the first qubit, is it 0 or 1? Right? So formally this means we measure the operator Z1, right? And then the thing is, of course, this has not a well-defined answer within this stage, right? And what it means is, right, that the answer is different for the two terms, right? And the first term would be 0 and the second one would be 1. So if you ask this question and get an answer, the state afterwards will be either 0, 0, 0 or 1, 1, 1. That's the destructive nature of measurements. But instead what we can ask, are the first two bits equal? Right? We ask a slightly different question, and then actually it's okay, it turns out. Because if you just ask, well, formally you measure an operator that is Z1, Z2, but the question you're asking just is, are the first two bits equal? Or equivalently, are the last two bits equal? And that actually has a well-defined answer within this state. Because it's the same in both, right? The first is 0, 0, 0, so all are the same. So the first two and the last two are the same. And the second term, again, they have a different value, but they are the same. So if you ask that question, we get a clear answer. And what this means physically is that if we measure this, if we really ask this question to nature and we get an answer, we can get this answer without destroying the state, right? Because we have asked the right question. And this may be the first weirdness of quantum mechanics that comes in here, right? And this is not important classically. We could also do this classically, right? It's a sensible question. But for classically, we don't have to do it. And quantum mechanics forces us to do that and nothing else. Okay. Second part of the repetition code. This is just a reminder of what we are doing so far. Now, let's consider, does this actually protect us from an error? It does. Let's consider one very special error, the bit flip. This is just the thing that flips 0 to 1 and 1 to 0, hence the name. It's also a Pauli X matrix, if you remember quantum mechanics 1. So what happens to the encoded state? Let's do a table and ask how do these measurements outcomes change. Imagine we apply a bit flip to the first qubit. What will be the state afterwards? Again, it follows from linearity, right? It will be 1, 0, 0 and 0, 1, 1. The first bit is now flipped in both. And now, of course, I can again ask, are the first two bits equal? And now the answer is no. But for the second one, the answer is still yes. The last two bits are still equal. Equivalently now, right, I can ask okay, what if I flip the second qubit? We already see a pattern here, right? So now the first two are not equal, and also the last two are not equal. So I get a different answer, actually, if I measure these things. And now, lastly, okay, what is the last thing that happened? The third bit could flip. And now the first two are equal, but the last two are not. And what, of course, is a very important observation here is that all these different possible errors have a different outcome for these measurements, right? So we can correct actually a single bit flip here in this code by doing these two measurements, and then depending on the outcome, right, if it was both equal, we would see nothing happened, we are good. If you get one of these outcomes, right, then you know you have to do something, and you even know what to do because you just have to reverse that error. So you apply another bit flip to cancel the first one that happened, right, accidentally. All right. Now, this is not quite yet enough. So you have to bear with me for another second. So let's do another repetition code. So what do I mean by this? Classically, there's only one, right? And I want to stress the fact that so far all the circuits that I've drawn to you, right, bit flips, C-naughts, they all make perfectly sense on a classical computer, actually. The only way quantum mechanics came in was through the input state, right, because we put an entangled state in the beginning. And now it turns out, and well, it's not surprising maybe, that if we want to protect quantum information, we have to actually do something quantum. And for that, let's start maybe with the circuit of the bit flip code that we had before, right? So at the dashed line here, the state of the circuit will be this logical state, alpha 0, 0, 0 plus beta 1, 1, 1. And then let's add a layer of so-called Hadamard gates. So what are Hadamard gates? You probably have maybe you have never heard of them, and this is because they have no correspondence on a classical computer, because they do a superposition. So they take the 0 state to a superposition of 0 and 1 with relative phase plus, and the 1 state to another superposition with a different relative phase minus. So on the Bloch sphere, this is a rotation by 90 degrees around the y-axis. And this is, of course, why it has not an equivalent operation on a classical computer, because a classical computer only lives on the poles, right? And now suddenly we are here on the equator of the Bloch sphere. Okay, so what does it do? So then our state afterwards is alpha plus 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 beta minus minus minus, right? This is just from the definition, basically, this follows. But what does it mean? What it means is, right, maybe it's simplest to understand maybe on the Bloch sphere picture, right? Because you can think of it as a rotation, really. And now if you think about now, here, there's these little labels X and Z on the Bloch sphere, right? One at the, unfortunately my pointer is not, right, there's this one and, okay, anyway. So I hope there's a Z and X label. And the rotation will swap the roles of the two. This is maybe the intuitive answer. But what I can tell you certainly is that the Hadamard does change the role of X and Z's. So it makes errors into checks and checks into errors. That means, okay, instead of these Z operators, we now measure a different kind of operators. If you tell us you're colleague in the lab, they can actually do it, right? And now suddenly, instead of a bit flip, I can correct a so-called phase flip, which is a Z error. Because I told you, right, there's different errors, right? A bit flip is the only thing that can happen classically. Quantum mechanically, a lot more things can happen, right? Again, on the Bloch sphere, a bit flip is a rotation by 180 degrees around the y-axis. A phase flip would be a 180-degree rotation around a different axis. Again, no correspondence classically. But again, it's a different error, and we can do it. Okay, so now we have a different code that corrects a different kind of error. And now, okay, what Shor did now is he defined something called the Shor code, and he said, why don't we do both? And this works the following. So we will concatenate the two. So we start with the phase flip code, right? This is just the circuit I had before, but drawn very largely. And why do I have I drawn this very largely, right? So this code we know corrects this phase flip error. So now we want to do also a bit flip. And what we simply do is we encode each of the constituent qubits of the phase flip code in a bit flip code. So concatenation just means that we have these kind of, this hierarchical structure, right? So we have 3 copies of a bit flip code and then a single phase flip code outside. So this is now a superposition. The output state will be a superposition of like 9 qubits. It's an entangled state of 9 qubits. And now, right, it looks like the phase flip code, where basically each constituent here, the minus bar, the bar indicates that these minus states are now themselves states on 3 qubits. Right? Okay. And it turns out, okay, this code can correct a single bit flip and a phase flip. So now 2 errors. So we have done a bit better. Right? And okay, again, if you want to tell this to your colleague in the lab, they have to measure a bunch of stuff. Right? They have to measure they have to always ask, okay, is now the first bit equal, the second bit equal, then the fourth and the fifth, and so on, right? So this is the inner checks. And then you also have to measure these big things, which are the checks of the outer code. Basically, we have to ask, are the first 2 pluses, right? But it's now you're asking, are there logical pluses? So actually what you have to measure is like this product of 6 operators. It gets more complicated for the laboratory. Right? They will not like that. But okay, we are theorists, for now we can do that. Okay. So now the real miracle that I promised you is that this is enough. Right? Correcting bits and phase flip is enough. We can now correct an arbitrary single qubit error, actually. And that is the really fascinating thing, I think, about it. And the essential insight for that is the following. So there is a math version and an informal version. So the math version is that the Pauli operators, that is x, z's, and their product, which is the Pauli Y matrix, and the identity, they form a basis of 2 by 2 matrices. And what does it mean physically, informally? That means that any operation, anything that happens on a single qubit is actually a superposition of nothing happening, the identity, of a bit flip, a phase flip, and both together. So I can view anything that happens on a single qubit as a combination of these 2 choices and both of them together, and nothing. Right? So now, apply this to a state. What does it mean? It really means, okay, anything happens to the Shor code state, right? And it's either the Shor code state, or it's a bit flip applied to it, it's a phase flip applied to it, or it's both applied to it. But I told you, right, we can correct a bit and a phase flip. But what does it mean? We correct these things by measuring operators and collecting the outcomes of the measurements. And we can correct these things because all the possibilities, all these three different possibilities correspond to different measurement outcomes. And what did I tell you about measurements, right? Once you look, the cat is dead or alive. So this is a very process of measuring these operators that discretizes the error. So we have this gigantic continuum of possible errors, but by measuring, we collapse this set onto a different set of outcomes. It will be after the measurement, right? The cat will be dead and alive, or here our errors will either be nothing happened, a bit flip happened, a phase flip happened, or both together happened, right? And this is really the miracle of quantum error correction, that kind of quantum mechanics is a combination of the continuous and the discrete, right? And this is why it works here, but it didn't work in the floating point case. Okay, maybe a preliminary summary, because in the second part of the talk, what I will want to do is I want to also give you a flavor of what people are asking today. Right? These are questions that people have answered in the 90s, which I think is very fascinating. But okay, let's summarize, right? So we have done the Shor code, and the Steen code has the same property. Actually, the Steen code is a better code to some extent. But again, it's more difficult to understand, I believe. The Shor code can correct an arbitrary single qubit error. Right? And there are versions of it. Now we can basically, right, we were in the Shor code, we repeated 3 times, right? We can now repeat it 5 times, 7 times, and we will actually be able to correct more and more. So this basically already gives a blueprint for how to do fault-tolerant quantum computation. Because now we have to make all our constituents these big superpositions of stuff. Right? And yeah, again, I want to remember that this is highly non-trivial, because fault-tolerant random access machines, for example, do not exist. And quantum error correction is really possible because quantum mechanics is not just wave mechanics. You might have heard that statement, it's not true. Quantum mechanics is really this dance of continuous superpositions of things, entangled states, but then discrete, that is technically projective measurements. Right? And it's really both that we need to do it. Right? All right. Very good. Should I take questions at this point, or maybe I can ask whether there's any questions already about the first part, because then afterwards we can go to the current research. Fantastic question. Not very efficient. It's possible. Okay, so there's 2 statements. There's a statement about numbers and there's a statement about scaling. The latter being very important. So the overhead is big, but it doesn't grow if you build a larger and larger computer. That's the key insight, I think. Right? So it's kind of bounded. It's a big number. But if you want to do Shor algorithm or so, you need 1,000 qubits, and that means 1,000,000 logical qubits. Something like that, right? So this is like the ballpark. For every qubit, you will have 1,000. For every logical qubit, for every actual qubit in your quantum computer, you will have 1,000 of these atoms. Right? But if you build a bigger quantum computer, you will not have to use more than that. Right? So if you want 1,000,000 quantum logical qubits, you still need thousands more. Yeah, not yet, but hopefully one day. I will show you what is the best what the best we can do, then you can judge. Yes, please. Into the measurement, you learned something. Noise is entropy is a lack of knowledge. Right? No, I mean literally, right? So we learned something about the system by measuring. That's where the entropy goes. Right? You learned a bit. That's how it's called entropy evacuation, I think, technically. So literally. Is that clear what I mean? So entropy is basically, right? I mean, entropy is a bunch of boxes, right? You say, in a magnet, right? You say, we have a magnetization, and there's a lot of microstates. But we don't know the microstate. So we only know the magnetization. That is the sum of all these things. Right? In that sense, entropy is a lack of knowledge, because we don't know what every atom does. Right? And also here, right, we basically, right, noise adds uncertainty, but we learn something by measuring.
So one of the problems with quantum computing, as I understand it, not very much, is that over time qubits decay. So
yes.
it's an approach where access memory, if you go through refresh cycles, you can stabilize data held in a quantum computer.
Yeah, exactly. So the idea is basically that you intersperse your computation with measurement of these called syndrome operators, right? These are these operators that I wrote down, like the Z1, Z2. It repeatedly asks these questions. And between the asking, you can actually do stuff, right? But you have to do this actually quite frequently. So there is a space and a time overhead that it's called, right? All right. So then let's look at what people are up to right now. Okay, so the first observation that I want to tell you is I titled this "Have Mercy with the Colleagues in the Lab" because I already told you, right, the Shor code is intuitive but not very practical. Because, for example, take the one size larger, right, where we repeated stuff 5 times. Then the Z checks will be okay, right? Also in the you always only have to ask about neighbors. But I already hinted at this fact that the other check of the outer code, they grow. Because you have to ask things about logical states. And these operators will get very hard to measure. So it's not a scalable thing if you want to do in the lab. Instead, you want to do something different, which is a bit hard to understand. But let me attempt to give you an idea of what people are doing. So what you want to do instead of the Shor code is something called a low-density parity check code. So because these are called parity checks, and low density implies that they have support only on few qubits. So you're not asking a question, is the product of these 5 qubits, or of these million qubits the same? But you only have to ask it about like a finite set. Right? And how do you do this? The most well-studied example is probably something called the surface code, where you arrange qubit on such a checkerboard pattern here. And okay, this has some size L. So this works for any size of grid. This is a grid of size 5, for example. And then, okay, you put the qubits on the vertices here, right, on these little circles. And then for each phase, you have an associated check, right? And you see that the phases are, it's a checkerboard, right? So they are, in this case, they are blue and red. And the blue checks correspond to measuring basically a Z check on the corners of the phase, whereas the red things correspond to measuring an X operator on the corners of the phase. And now this, okay, hopefully you see that at least in the setup you will at most measure 4-body operators, so that's much better for our experimental colleagues. And also it will protect, for an arbitrary size, it will protect L12 rounded down, right? So this is the floor function, this angular brackets. It will protect against any error acting on at most L12 qubits. So you build this of size 5, you can, for example, correct 2 errors. All right? So, yes. So this looks much more tractable. Indeed, this has been built. So this is a fantastic experiment done very recently, actually. At least now we are jumping ahead a long time, from 1994 to 2022, where the ETH group, this is the group of Andreas Wallraff, the Quantum Devices Lab that I mentioned before, they have actually built a 3x3 version of this. This is a sketch. This is actually a picture of the circuit, right? Because it's an academic group, we actually get a picture in a publication. It's fantastic. So I can show you this. And you see here, these little stars are basically the qubits. There's a few more. I will probably not have the time to fully explain why. But let's just superpose this thing with the sketch that I do this. So it's rotated by 45 degrees. And so this is really a chip. These are aluminum wires, basically. They get superconducting. This is how you perform the computation. And then all these colored lines are microwave electronics that you use to control this chip. Okay, Google has much more money than academia, so they have even built 2 of these things. And they have built a size 3 one and a size 5 one. And this is a plot. So we don't have a picture because they are not academia, unfortunately. So they don't give you pictures anymore of their chips, of the newer models. So we don't know how this device looks in practice. But they have on their blog, they actually did publish this nice plot where they compare the performance of the smaller and the bigger code, right? And I told you, maybe now going back to the coffee example, right? If you repeat more, you want to be better at correcting. And then you see, okay, so they built this chip, and they have actually built a bunch of chips. And each chip has a distance 3, or so a size 3 code, and a size 5, right? Because you can just ignore part of the 5 code, and you have a 3 one, right? And each of these dots is a single, in this plot, is a single device. And on the x-axis, we have the fidelity of the distance 3 code. And on the y-axis, you have the fidelity of the distance 5. So distance is the same as the size. It's just a technical term. And you see, okay, you want to be above the diagonal if quantum error correction is supposed to work. And you see their very best device is a bit better if you scale it up. So they are really just scratching the surface of quantum error correction being possible, right? And y actually can get worse if you make it bigger. Basically, if your device is too bad, you are making it worse, actually, if you scale it up. Because errors accumulate even more, and you have to fight that. And maybe now the question is, maybe connecting. So I've promised in my abstract, I believe, to connect quantum error correction to what my original specialty is, that is condensed metaphysics. And condensed metaphysics come in if you want to model the statistics of these devices. Because now you can ask how many errors are actually too much. So how good do your constituents have to be for error correction to work? And formally, the statement is that there is a threshold. So you have some phenomenological parameter describing your noise, that is p error. And it has to be smaller than some critical value. And actually, then the statement is, okay, if you make your code bigger and bigger and you are below the threshold, so your computer is good enough, then encoding will help, and the failure rate of the code will go to 0 as you make the code larger and larger, right? So as you scale up your surface code here on the left, right, your cat gets sharper and sharper. Right? And this is really a quantum state that you are stabilizing, right? So the cat is both dead and alive here. But if you are not good enough, then actually you make it worse by encoding, right? And this, some of you have a background in condensed metaphysics, this might remind you of the behavior at a phase transition. And this is because this is a phase transition. And in fact, okay, this is a very, very complicated process to model, but remarkably, you can map it exactly under certain assumptions on a condensed meta system, and a very old one. So the certain assumption of the noise, this process for the surface code, for this thing that has only very recently been built, maps exactly onto a well-known model in physics. And you can describe this process by looking at something called the random bond-Ising model. And this is remarkable because the random bond-Ising model is a very, very old model of condensed metaphysics. It has been devised by Philip Warren Anderson of Princeton, one of the giants of the field, to describe the interactions of magnetic impurities in metal alloys. Right? And this model remarkably describes this phase transition as well. So the formal statement is, okay, you draw a phase diagram of this model that describes like magnetic impurities. And these magnetic impurities can become, basically they are magnetic and there's a non-magnetic phase. Right? There's a ferromagnetic phase and there's a non-ferromagnetic phase. And then it turns out if you compute the phase diagram of this model, right, it has two axes. There's a disorder strength, so you have like some dirt in the model. And then there's temperature. And basically the statement is that the largest amount of noise that your code can tolerate is actually exactly equal to the largest extent of this ordered phase that are indicated in red if you project it onto the x-axis, which is the disorder in this model. Right, so then this is a remarkable connection where you can learn something new about this quantum system by mapping it exactly to a very old model system used in condensed metaphysics. Maybe now in my last slide, I want to tell you a bit about what I do. So what is a bit active research question in quantum error correction is developing better codes. And one example of that I want to tell you about is hyperbolic surface codes. And what is the recipe? So they are complicated beasts. They look mesmerizing. Escher liked them, like these patterns as well. But really what you should interpret is, this is basically your circuit layout. So you have to put a qubit, not now on a square grid, but you have to put them on each edge of this picture. And then the statement is, okay, of course, this is harder to build. You also have to define some checks. I don't want to go into so much detail in this. But again, they are local, and there's some description based on the graph. And they are harder to build, because they're not naturally embedded, right? It gets very crowded to the edge if you go to the edges of this plot. But if it is built, it has a much reduced overhead. So this connects maybe to one of the previous questions that we had. The toric code has a lot of overhead. A single qubit will be encoded into this grid, right? If you have a 10 by 10 grid, right, 100 atoms, for example, will be one logical qubit effectively. The promise is if you do it by this, not on a square grid, but on this geometry, what you will get is, if you make it bigger and bigger, you will not only protect information better, but you will also get more qubits encoded. So the information gets better and you encode more, right? This is called what is called, maybe some of you know code theory, it's called a finite rate code. And of course, in principle, this can be built. So this is a beautiful picture of an artificial hyperbolic lattice, also made from superconducting resonators in the laboratory of Andrew Hauck in Princeton from this publication. So in principle, you can realize such a geometry even in the lab. And then maybe one result that I did, for example, is now you can ask, okay, can we again, for these codes, model the error correction process? Can we map it to some model of condensed matter physics? And indeed you can. It maps on, well, a very complicated model that lives in curved space, so on a negatively curved space. These were models that maybe in the past had been only studied, but mostly studied actually by high energy physicists, right? Because the universe kind of is a negatively curved, well, it's supposed to be maybe a negatively curved surface. And it turns out, okay, we could map it exactly, and this mapping kind of then allows us to calculate for these kind of codes the optimal, information theoretically optimal performance that you can get at a certain size and at a certain strength of noise. And remarkably also, this actually yielded some new insights into the statistical mechanics of these models. So you cannot only learn basically about new systems by an old theory, but you can actually also learn from new systems about an old theory. So that is very, very nice, I thought. Okay, and with that, I have reached my summary. So hopefully I've convinced you that quantum error correction is indeed possible, which is surprising. And I also introduced the threshold theorem, which says, okay, QC, the constituents have to be good enough. The experimental state of the field is okay. We are just scratching the surface maybe of the threshold. And I've also told you about some current research that I am doing, just to connect with the theme. Oh, thank you very much. I want.